You know all that time travel stuff you see in the movies? I'm not talking about DeLoreans or weird phone booths. I mean, could it be real? Well, it turns out traveling to the future is actually possible. And the secret isn't some made up device, it's speed. So let's break down exactly how this works.
Okay, let's kick things off with a scenario well, it's pretty mind-bending. Imagine this. You hop on a spaceship, fly around for what feels like 2 years to you. But when you get back, everyone you know, your friends, your family, they're all 14 years older. So is that just a cool plot for a sci-fi movie, or is there something more to it?
Nope, it's not science fiction at all. It's real, it's proven physics, and this truly bizarre effect, it's a core piece of one of the most famous theories in history, Albert Einstein's theory of special relativity. So yeah, in this explainer, we're gonna dig in and figure out exactly how this is possible. All right, so to really get our heads around how speed can mess with time, we have to start with one fundamental, unbreakable rule of the universe. And I gotta warn you, it's a rule that kind of breaks our everyday common sense, but believe me, it is the key to everything else. First things first, we've got to talk about something called a frame of reference. And really, all that means is it's your point of view. Think about it like this. You're on a train, and it's moving super smoothly. To you, you feel like you're just sitting still, right? And the world is just whizzing by outside the window. But for someone standing on the platform, well, they see you moving. And here's the wild part. Physics says you're both right. Motion is all relative. And here is the absolute crucial point. While your motion is relative, there's one thing in the entire universe that is not. It's absolute. And that's the speed of light. I mean, it seriously doesn't matter if you're standing still, riding that train, or blasting off in a rocket ship. If you measure the speed of light, you will always get the exact same number. It is the universe's ultimate unbreakable speed limit. Okay, this whole speed of light is constant thing, it leads to some really strange results. So let's try a little thought experiment. You've got a spaceship, and it's traveling at half the speed of light. And then it fires a laser beam straight ahead. So for someone just standing on the ground watching this happen, how fast is that laser moving? Now, common sense, our gut feeling, tells us to just add the two speeds together, right? The speed of the ship plus the speed of light. But that's totally wrong. The person on the ground would see that laser moving at, you guessed it, exactly the speed of light. Nothing more. You literally cannot make light go any faster. And it's this one weird fact that forces time itself to stretch and bend. So if the speed of light can't change, something else in the equation has to give. Something has to be flexible. And that something is time. I know, it sounds crazy, but let's see how this works with another classic thought experiment. We're going to use something called a laser clock. Okay, so picture a clock that works by bouncing a beam of light between two mirrors, up and down tick-tock. Now, our astronaut Monsi is inside her speeding spaceship. From her point of view, she just sees the light going straight up and straight down. A nice, short, simple path. But for Kelsey, who's watching from the ground as her ship zips by, he sees something different. For him, that light beam has to travel a much longer diagonal path to get from one mirror to the other. And here's the whole point. Since we know the speed of light is the same for both of them, but Kelsey sees the light travel a longer distance, what's the only possible explanation? It's that more time must have passed for Kelsey to see that happen. And that is the absolute core of this whole thing. For every single tick that Monsi's clock makes, Kelsey's clock has ticked, well, more than once. From his point of view, her clock and her time is literally running slower. This effect has a name. It's called time dilation. It's the stretching of time because of motion. The faster you move through space, the slower you move through time, at least compared to someone who's standing still. Okay, I get it. This all sounds pretty theoretical, pretty abstract, but does it actually matter in the real world? Like, by how much? Well, let's dive into the numbers and see just how this effect scales, from something tiny to something, well, massive. Let's start with something we can all picture. Astronauts on the International Space Station. I mean, they're moving incredibly fast, right? Something like 17,000 miles per hour. So does that mean they're time travelers? Well, yeah, they are, but only by a tiny little bit. For every 6 months they spend zipping around up there, they age about 0.007 seconds less than we do down here on Earth. So yeah, it's a real measurable difference, but maybe not quite blockbuster movie material. At least, not yet. So what happens if we could really crank up the speed? Let's go back to that sci-fi scenario we started with. Let's imagine we could travel at 99% of the cosmic speed limit. At that incredible velocity, time slows down by a factor of about 7. Let that sink in. For every one single year that passes for you, the traveler, 7 years would pass back on Earth. So that question from the very beginning, it was spot on. A 2-year trip for you means a full 14 years have gone by for everyone you left behind. Now, even with these numbers, you might still be thinking, this is all just some weird mathematical trick. But I promise you, it's not just a theory. Time dilation is a real observable thing, and it's actually crucial for technology you and I use literally every single day. Let's just look at the proof. First up, GPS. The satellites orbiting Earth are moving so fast that their onboard clocks actually run a tiny bit slower than the clocks down here. Engineers have to constantly correct for this time difference. If they didn't, the GPS on your phone would be off by miles every single day. For real. Second, we've actually measured this with people. Astronaut Scott Kelly spent about a year in space, and when he came back, he had aged microseconds less than his identical twin brother, Mark. And finally, we see it all the time with tiny particles from space called muons. They have super short lifespans, they should decay long before they ever reach the ground. But they're moving so close to the speed of light that their internal clocks slow way down, giving them just enough time to make the journey. And this really gets to the heart of what relativity is telling us. You know, we all tend to think there's just one clock for the whole universe, ticking away at the same rate for everyone. But that's just not true. It's a misconception. As one physicist puts it, there is no objective time. Time, just like your speed, depends entirely on your frame of reference. The way you experience time literally depends on how you're moving through the universe. Okay, so if time travel to the future is physically possible, why aren't we doing it? Why aren't we building starships and booking one-way trips to the year 3000? Well, as you can probably guess, there are a few pretty major catches. Yeah, the laws of physics throw some serious roadblocks in our way. First, there's the energy problem. The faster you go, the more energy it takes to speed up even a little bit more. To actually reach the speed of light, you need an infinite amount of energy. So that's a no-go. Second, space isn't actually empty. Hitting even a tiny speck of dust at those speeds would be like a bomb going off. It would completely destroy the ship. And finally, you have the acceleration problem. You can't just hit a button and jump to 99% light speed. The g-forces would crush you. You'd have to accelerate slowly and then decelerate slowly, which would add years and years to the trip. So here's the bottom line. Special relativity shows us that time travel to the future isn't just science fiction. It is a very real consequence of the laws that govern our universe. The faster you go, the farther into the future you leap. But, and this is the big but,